In section 1.3, we're going to talk about graphs of functions. So some things we'll look at are finding domains and ranges and using vertical line tests, determine intervals on which functions are increasing, decreasing, or constant, look for relative maximum and minimum values, talk about graphs of step functions and piecewise functions, and then just define what an odd and an even function is. So remember, when you have the graph of a function, it's really just the set of ordered pairs where your x values are your domain and your y values are your range. But instead of using y when we're in function notation, we write y as f of x. So remember, x is the directed distance from the y-axis, and then f of x is the directed distance from the x-axis. So in our first example, if we're just finding the domain and the range, and remember, domain, you're looking at what are your x values, and range, you're looking at what are your y values. So we'll use the graph to find the domain, the range, and then a few actual points on the graph. So for part A, where they ask for the domain, if you notice, our graph doesn't go on forever. So we have a closed circle here where it's starting and an open circle here. So remember, closed circle means it contains the point. Open circle means it does not contain the point. So if we look, our x-coordinate starts at -1. So for our domain, we would say we go from -1 all the way up, and it's continuous until we get to when x is 4. But we have an open circle at 4, so it wouldn't include 4. If we skip to part C for our range, we're looking for our lowest y-coordinate, which in this case is -5. And our highest y-coordinate is actually up here at the top, and that's 4, and it includes that point. So we would say our range goes from -5 to 4. And then part B, when it asks us using function notation f of -1, that means when x is -1, what does y equal? So we would look at this point. When x is -1, y is -5. F of 2 means when x is 2, what is y? And again, we're looking up at this point. So y would be 4. I don't think it asked us for any other ones. So our next example, finding domain and range of a function. So let's say we don't have a graph, and we touched on this a little bit in the last section. When we have that square root, remember, anything under a square root, that the square root of x, remember, has to be greater than or equal to 0. The x value underneath does. So when you have the square root, what we can do is we can take what's underneath the square root and set it greater than or equal to 0. So if we know that x minus 4 has to be greater than or equal to 0, then x has to be greater than or equal to 4. So your domain, if you were writing it as an inequality, you would say x is greater than or equal to 4, or you would say 4 to infinity if we were using interval notation. Now the range, if we think about plugging values in, if our lowest number is 4 and we plugged a 4 in for x, we would get 0 for y. And then if we plugged a 5 in for x, so if we kept plugging bigger numbers in, our y values would keep getting bigger. So in this case, our range, we would say, goes from 0 to infinity. So the graph of a function says, by definition of a function, at most one y value corresponds to a given x value. So this is the vertical line test. If you can draw a vertical line through the set of points on a coordinate plane, and no vertical line intersects the graph at more than one point, then your graph is a function. So increasing and decreasing, these are really formal definitions. Really what this means, an increasing function. So if you're going from left to right, we always go from left to right. And an increasing function just means that your graph is increasing. So as x values get larger, your y values are also getting larger. Decreasing means that as x values get larger, your y values are getting smaller. And constant would mean that as x values increase, your y values are staying the same. So we have three graphs. Determine open intervals. So open intervals means we're not going to include the endpoints, on which each function is increasing, decreasing, or constant. So if we look at this first one for letter A, we do have this one little part that's kind of looks like it's flat here, but we're going to consider that just to be all this continuous part. So for this graph, we would just say it's increasing from negative infinity to infinity. Even at that little teeny tiny flat part, there's not really a starting and an ending point where it starts to be constant and then it stays constant. If you were to really zoom in on that, it would look like it actually continues to increase the whole time. So for graph B, increasing would mean when we're going up, so we would look at this interval, and this interval would be your increasing. So our increasing intervals, we would say is negative infinity to negative 1. When you're using interval notation, make a note to yourself that you only use x values. You never put y values in your interval notation because then it turns it into a point and not an interval anymore. So going back to B, so we're increasing negative infinity to negative 1, and then from 1 to infinity. And then in this one, you would be decreasing from negative 1 to 1. If we look at the piecewise function for part C, we have increasing, INC, from negative infinity to 0. We would be decreasing here, so we would be decreasing from 2 to infinity, and then from 0 to 2 would be when our graph is constant. So the next thing we're going to look at are the maximum and minimum values, and your maxes and mins occur when your graph changes from increasing to decreasing or to constant behavior. So really when it's kind of changing direction. You can think about it if you were out for a hike, if you went from walking uphill just to flat ground, or flat ground to downhill, or downhill to uphill, any of those changes of direction would be your maximum and minimum values. And we call them relative because you could actually have more than one. So we wouldn't say it's the only one, we just say it's a relative max or a relative min. So if you look at this figure here, we have several different examples. So if you notice, these 2 points right here are relative minimums because you're changing from decreasing to increasing. And at the top of the hills there would be your relative maximums. So what I want you to do is to take out your calculator, and in your y equals, I want you to graph this function negative x cubed plus x. And when you're graphing it, if you look at this axis that's given to you, notice that your window should be going from negative 6 to 6 for both your x and your y axis. And so then when you hit graph, you should have a graph that has, it goes kind of decreasing, increasing to decreasing. So go ahead and graph that and then sketch your graph on the axis. And so now as you're sketching your graph, you probably hopefully noticed that your intersection points on the x-axis are at negative 1, 0, and 1. And between negative 1 and 0, it has a minimum. So on your calculator, you're going to go into second calc. So to find that minimum, in your calculator, you're going to go to second calc, choose minimum, and then put your cursor to the left and hit enter, put it to the right and hit enter, and then hit enter again. So it guesses that your minimum is negative 0.577, negative 0.385. And so then you would graph a point on your graph kind of about there. And then to find the max, which is going to be between 0 and 1, you're going to go to second calc and max. And again, when you go to second calc and max, you're going to put your cursor to the left of the maximum and then to the right of the maximum and hit enter when it says guess. And we find out here that it guesses that our maximum is at 0.577, 0.385. So we have some symmetry there. And so then we would sketch that point. And then what you would do is you would just kind of sketch your graph through those points that you drew right? And this goes on forever. So by doing that and using our calculator, this problem wanted us to find the relative max and min, which was what we found here. That was your minimum and that was your maximum. And when you're writing maximum and minimums, unless it says otherwise, you're going to write them as an actual point with an x and a y coordinate for both. So that way you could graph that actual point on your graph. So then we move into step functions and piecewise functions. A lot of you up to this point, your step function has looked like this. It's kind of that rounding down function. This book uses the notation where it has kind of this double bracket for your x, and that is called the greatest integer, but what it does is it rounds it down. So like -1/2 would round down to -1. 1/10 would round down to 0. 1.5 would round down to 1. So if you see that notation, that's what that means. And so if we were to graph that as a step function, so sometimes step functions are helpful when you graph them in making a table because it can be a little bit confusing. So first, if we were graphing this function, we'd say if x is 0, y is 0. But then don't go to the next integer, go to something in between. So if x was 0.5, your y would still round down to 0. So we would know that 0, 0 is included, and everything up to 1 would be included, except for 1, because at 1 we would have an open circle. So everything from 0 to 1, not including 1, your y value will be 0. But then at 1, those values jump up to 1, and everything from 1 to 2, but not including 2, and then it jumps up to 2, and 2 to 3, not including 3, and then it follows that same pattern in the other direction as well. And so over here we have that your domain is all real numbers. Your range is just integers because it's always going to round down to an integer. Your x-intercepts is the interval from 0 to 1, right? So this whole interval is your x-intercept here. Your y-intercept is at the origin. We have a constant between each pair of consecutive integers, and it jumps vertically 1 unit at a time. So then we have piecewise functions, and these are always kind of tricky to graph, but what I want you to do when you graph these is just to graph these as two separate functions. So I'm going to use two colors. So I'm going to graph the first one here, 2x plus 3, but only for when x is less than or equal to 1. So again, sometimes making a chart can be helpful. So if x is less than or equal to 1, we're going to start when x is 1, and if we were to plug a 1 in, we would get 5. And now let's pick numbers that are less than 1. So if you plugged a 0 in, you would get 3, a -1, you would get 1. And so then if you were to sketch that, if you graphed the point 1, 5, 0, 3, -1, 1, we can draw a line, but we're only drawing it towards the negative x values. So then the second piece of this graph, we're going to sketch this. And again, if we made another table, so we're still starting when x is 1, and if you plugged in a 1, you would get a 3. But because it doesn't include it, that 0.13 when you draw it will be an open circle. And then we pick values greater than 1. So then if you pick 2, you would get 2. So if we plotted the point 2, 2. If we plotted the point 3, we would be 1, so 3, 1. And so we get a graph then that goes in the opposite direction that way. So it's still a function, it still passes the vertical line test, but it's really just two different pieces of functions. And then the last thing is odd and even functions. So a graph has symmetry with respect to the y-axis. So that would mean if you had a graph here, symmetry with respect to the y-axis would mean that the point reflects across the y-axis. So if you had a point here that was xy, in a graph that was symmetric to the y-axis, you would also have the point -xy. If it has symmetry with respect to the origin, that means if you were to revolve it 180 degrees around the origin, you would end up with that same point in that other quadrant, opposite quadrant, but your x and y values would be opposite. And then if you have symmetry with respect to the x-axis, again, that point xy would reflect across the x-axis. So your x would stay the same, but your y would become opposite. So what we find is that points that have respect to the y-axis are even. So if we were to go back up here, a graph that looks like this would be even, an even function. Origin, if you have symmetry around the origin, it's an odd function. And if you're symmetric with respect to the x-axis, it's actually not a function because it wouldn't pass that vertical line test. So if you look at these three graphs, the first one here, if you notice this point xy reflects over to this point here, so that would be an even function. This point would reflect over around the origin, so that would be the odd function. And then the last one is when you have that reflection symmetry across the x-axis and it's not going to be a function. So we're just going to determine even and odd here. So again, the even idea is if you folded your paper along the y-axis, would the graph fold on top of itself? And for A, it would. So we would say that this is even. For B, if you were to flip it completely upside down, would it look the same? And if it does, then it's odd. Or the idea that does this point become the opposite point down here? For C, we don't have symmetry across that y-axis. So this would be neither. So be careful that just because it has an even degree doesn't automatically make it an even function. And just because it has an odd degree doesn't make it an odd function. And if you look at D, again, we have that symmetry. So this would also be even.